Good morning, good afternoon, good morning, students. So, last class we discussed about the electrical technology unit number 3, transformers. So, discuss about the principle of operation of transformer, construction of transformer, and next EMF equation of a transformer, and some problems on EMF equation. Generally, what is the transformer? Transformer is a static device which transfers electrical energy from one circuit to another circuit without change in frequency, with change in voltage and current. The main principle involved in transformer is mutual induction principle. That is, it is based on the electromagnetic induction principle, that is mutual induction. So transformer having primary winding and secondary winding and core, right? Now first of all, go for the principle of operation. Generally, just brief discussion about last class, just 5 minutes. So whenever we are giving a AC supply, alternating current, alternating supply to the primary winding of a single phase transformer, it may directly flowing through the alternating current, primary current to the primary winding. Whenever the primary current will flowing through the primary winding, it may produce alternating flux. That alternating flux, the flux is alternating, that's why that may be linking with the secondary winding. So because of that linking the flux in the secondary winding, an EMF is induced in the secondary winding. Because of that induced EMF, and secondary current is flowing through the load circuit. So this is about principle of operation of single phase transformer. And then construction means it consists of winding, that is primary and secondary winding. It consists of iron core. So, and is also it consists of core cell. Core means core type and shell type. Construction wise, core type, shell type, and construction, winding, core, book hole relay, conservator, oil, breather, and also inlet valves and outlet valves, that is nothing but bushings. All these things will be discussed clearly. What is the function of winding to carry the current, and what is the function of core, what is the function of conservator, what is the function of oil, what is the function of book hole relay, what is the function of breather, what is the function of radiators. All these things will be discussed in last class. And then go for the EMF equation of a DC generator, EMF equation of a single phase transformer. We have to derive the EMF equation, that is E1 is equal, for primary winding, E1 is equal to 4.44 F N1 pi, E2 equal to 4.44 F N2 pi volts. So these two equations, combination of these two equations we can call it as EMF equation of a single phase transformer. And we have to determine the EMF equation for a given problem, and also from that EMF equation we have to determine the flux also, flux per pole. Otherwise, sometimes they are asking number of turns in primary, number of turns in secondary, and sometimes they are asking current in the primary winding, current in the secondary winding, right? So like that, last class we discussed it clearly. Now another topic, that is the transformer on load condition and also on no load condition. Very important, very important topic, very important question also. There is no load, what is the behavior of transformer? If it is a load, what is the behavior of transformer? Now we have to discuss it clearly now in this class. So mainly no load on load is nothing but generally ideal transformer, practical transformer, whatever it may be. And some phasor diagrams also I have to discuss it clearly. So first of all, we go for the ideal transformer. Ideal means there is no losses. Ideal person means, so you have to follow the ideal person means they have some qualities, some good qualities. Because of that, we have to select ideal person. Similar manner, ideal transformer is nothing but there is no having any leakage flux. That means the flux produced in the primary winding or it may be in secondary winding because of currents, that may be primary or secondary currents. So the flux is 0. There is no leakage current such that there is no leakage flux. Second property is the winding, primary winding or secondary winding does not having any resistance. That means there is no drop in the primary and secondary winding. That means voltages are equal, applied voltage and induced voltage. That means so applied voltage in the primary winding and induced voltage in the secondary winding both are equal whenever there is no resistance in the winding. Because there is no resistance drop means there is no losses. There is no losses means input is equal to output. Input is applied voltage, output is induced voltage. And next, the core has infinite permeability. The core has infinite permeability. That means reluctance of the core is 0. A negligible current is required to establish the flux in it. As usual, lossless magnetic core. Lossless means there is no hysteresis loss, there is no eddy current losses. We already discussed in the losses occurred in the core is nothing but iron losses. That is, iron losses are two types, hysteresis and eddy current losses. Now, for ideal transformer, there is no hysteresis and there is no eddy current losses. So now go for the ideal transformer on no load condition. Look at the figure. Applied voltage V1, applied current is I1 and EMF induced in the primary winding is E1. Number of turns in the primary is N1 and this is the primary winding and this is the secondary winding. Number of turns in the secondary winding is N2. Induced voltage in the secondary winding is E2, that is equal to V2. Load current, there is no current, that is I2 is 0. Why? So it is no load, there is no load. There is no load means there is no current, I2 is 0 and flux is pi. If I2 is 0, that means there is no load and primary winding may draw some extra current, that is magnetizing current IM, that may introduce the flux. As the transformer is ideal, the pure inductive nature, completely inductive nature, there is no resistance, right? Transformer is ideal is nothing but winding has no resistance, R is 0, that means completely in inductive nature. Look at this. So we have to draw the phasor diagram. First of all, I have to take the reference as flux. Flux is always proportional to current, that is nothing but this is the magnetizing current. Now before that one, applied voltage E1 is always lagging the flux by 90 degrees. And E2 is always lagging. Why? Because it is resistance is 0, that means totally inductive nature, that is also E2 is always lagging by 90 degrees by E1 or flux, whatever it may be. Now what about V1? V1 is nothing but flux, sorry, terminal voltage applied by the supply, from the supply, that is nothing but always. So Im produce flux phi, which is in phase with Im. The flux link with the both windings causes induced EMF E1, E2 are always lagging. According to Lenz's law, the EMF induced is always opposite to that of supply voltage. That's why EMF are lagging by the flux, therefore terminal voltage is leading by the flux, that is 90 degrees. Now, this is the most important. Practical transformer on no load condition. When the transformer is on no load condition, the primary input current under no load condition as to the supply. That means it may produce some losses, that is iron losses in the core. As usual, iron losses contains hysteresis and eddy current losses and very small copper losses in the primary. Hence, no load primary current I0 is not at 90 degrees, bend V1 but lags it by an angle less than 90 degrees. Now the no load current has two components. One is working component or core loss component. Another one is magnetizing component. So it is required to produce the flux. Two components, IW and IM. So look at the figure, circuit diagram. So this is a practical. Ideal transformer means there is no resistance in the primary, right? That's why exactly 90 degrees phasor diagram. But it is a practical diagram, practical transformer. It is having some resistance, small resistance. So that's why it is having some drop. That's why it is not exactly 90 degrees. So it is having less than 90 degrees, the phase angle. So as usual, V1 applied voltage, E1 induced EMF, I magnetizing current, that is no load current. Now taking the phasor diagram, I mean, so this is a flux as reference, and as usual, E1, E2 are lagging by flux by an angle 90 degrees, and V1 is always opposite to the top induced EMFs because of Lenz's law. Now the no load current may having two components, that is magnetizing component and core loss component or working component. As said earlier slide, the magnetizing component is used to required produce the flux. It is required to produce the flux. That is nothing but the magnetizing current is in phase with flux. Flux and magnetizing current both are in same phase. That's why I am putting I magnetize here. Now working component or core loss component is always in phase with terminal voltage. Now the phasor sum or vector sum of magnetizing component of current and working component of current is nothing but no load current. Look at the figure. Now the angle between terminal voltage and I0 is nothing but no load phase angle pi naught. Now from this phasor diagram or from this no load operation of a practical transformer, we have to determine magnetizing current, working component current or core loss component current, and also no load current, and also no load phase angle, and also no load power factor. After determining the phase angle pi naught, we have to determine the power factor easily, and also iron loss values also. That is IW is equal to, from this, look at the figure. What about cos pi naught? Cos pi naught is equal to adjacent by hypotenuse, that is IW by I naught. Sin pi naught is equal to opposite by hypotenuse. Opposite is nothing but Im. This Im is equal to this one. So Im by I naught. So Im is equal to I naught sin pi naught. IW is equal to I naught cos pi naught. So you have to adding hectorically I naught is equal to square root of IW square plus I magnetizing IM square. So working component IW is equal to I naught cos pi naught. IM magnetizing current IM is equal to I naught sin pi naught. Therefore, no load current I naught is equal to square root of IW square plus IM square. The primary power factor at no load is equal to, that is nothing but cos pi naught. We know that power factor is the ratio of active component of current to apparent power, active power by apparent power. So similarly, IW by I naught, right? And no load power or iron loss, no load input power, P is equal to V1 I naught cos pi naught, very, very important. So these formulas are very, very important as competition exam wise or also for our B.Tech point of view, they are asking problems. Sometimes they are asking theory, explain the transformer on no load condition and load condition, 10 marks. Otherwise, they are asking draw the phasor diagram of transformer on no load, 2 marks, very, very important. Draw the phasor diagram for single phase transformer on no load condition. That is, flux is reference and lagging induced voltages E1, E2 are lagging by flux by 90 degrees. V1 is exactly opposite to that of induced voltages because of Lenz's law. The no load current is a combination of active component of current and magnetizing component of current, that is IM square root I naught is equal to square root of IW square plus AM square. Simply we have to draw the phasor diagram for 2 marks. Otherwise they are asking problem by using this one. Determine the working component of current, determine the magnetizing component of current, determine the no load current, or determine the power factor at no load, or determine the no load input power, or determine the copper loss, whatever it may be they are asking. So from this no load analysis, we have to determine the shunt branch parameters also. In the equivalent circuit, so you have to determine the shunt branch parameters, that is R0, X0, no load resistance, no load reactance. So that is V1 by IW, R0 is equal to, we know the V1 value, we know the IW value, V1 by IW, and reactance X0 is equal to V1 by IM. Now this is about transformer on no load condition. Now go for the transformer on load conditions. Transformer on load conditions. Before putting the load, I2 is 0. Now we have to we are connecting the some load on the secondary side. Now the secondary current is also flowing, right? Whenever a certain load is connected to the across the secondary winding, then an I2 current is flowing through the load circuit. The phase angle of secondary current I2 with respect to the V2 depends upon the nature of load. That means the angle between these two I2 V2 is lagging or leading or in phase. That may be depending upon the different types of loads: resistive load, inductive load, capacitive load. If it is a resistive load, what is the angle between voltage and current, secondary voltage and secondary current? Resistive load, voltage and current both are in phase to each other. The phase angle is 0 degrees. That is nothing but unity power factor, right? So both are in phase. But coming to the inductive, so I2 is lagging some angle by V2. If taken as a capacitive load, I2 is leading with some angle by V2, right? So resistive load is nothing but UPF, unity power factor. Inductive load is nothing but lagging power factor. Capacitive load is nothing but leading power factor. Now, as usual, neglecting the winding resistance and leakage flux, right? So look at the figure. Figure A will gives the no load condition. There is no load on the secondary, but whenever you are giving the supply, the current will flowing, that may produce the flux. That flux is alternating, that's why it will be linking with the secondary winding. Suppose we have to connect the load and I2 current. Here from figure A, I2 is 0. There is no load, that's why. Now coming to the I2, when connected load, I2 is flowing through the winding. Here also it may produce some another flux. Please clearly listen. At no load condition, because of primary supply voltage is connected across the primary winding. That means a supply voltage is connected across the winding and primary current is flowing, that may produce primary flux pi. Now if you are connecting a load, that may produce I2 current, right? I2 current. That I2 current will set up extra flux that may be flowing from secondary winding to primary winding. But first figure, primary winding produce flux, that flux is flowing from primary to secondary in this manner. Clearly, please show the figure and also clearly listen. The primary current, whenever you are giving the primary current to the primary winding, it may produce some flux, primary flux pi, that may be flowing from primary winding to secondary winding. Now you are connecting a load on the secondary winding. Whenever you are connecting the load on the secondary winding, a secondary current is flowing, right? Now that secondary current may produce another flux. That flux is secondary flux, that is pi 2, indicated as pi 2. That may be flowing from secondary winding to primary winding. Look at the figure. So this is the primary winding pi. It is flowing from primary to secondary, and now because of I2 and secondary flux is flowing, that is pi 2. Now coming to the figure C. Because of secondary flux is flowing from secondary to primary, now this pi 2 will cause of production of extra current, that is I1 dash, leakage current I1 dash in the primary winding. Because of that leakage current produced in the primary winding, that leakage current is also produce an extra flux pi dash, an extra flux pi dash, that is flowing from primary to secondary, that is flowing from primary to secondary pi dash. So this indication is wrong. So pi dash. That means here three fluxes are there without load because of primary winding supply, and flux is flowing from primary to secondary, that is pi. Because of load and I2 current, load current is flowing. Because of that load current, and secondary flux is flowing from secondary to primary, pi 2 as shown in figure B. Now that pi 2 is, whenever that pi 2 will touches the primary winding, that may produce an leakage current I1 dash. Because of that I1 dash, an extra current is, extra flux is produced, that is pi 1 dash, that is flowing from primary to secondary, shown in figure C. The flux produced in the figure B, the flux produced in the figure C, both are opposite to each other. Both are opposite to each other and they cancel to each other. Then the remaining flux is the main flux only. Main flux. So this is the transformer on load condition. What are the fluxes produced and they are cancelled to each other? For a secondary flux, because of secondary current or load current, cancel to leakage flux because of leakage current. Both are cancelled to each other and main flux is remaining, right? Look at the once again. When the transformer is on no load as shown in figure A, it draws no load current I0 from the supply. That may set up flux in the core, that is pi. Next figure B. When the transformer is loaded, current IT is flowing from the secondary winding. This current I2 produce an MMF N2 I2 will set up the flux. That is the pi 2. Because of Lenz law, pi 2 is always opposite to the main flux, right? Shown in the figure B. Now, an additional current I1 dash produced with the help of pi 2 and they produce additional flux pi 1 dash. That is also same direction of pi, right? So pi 1 dash and main flux both are same direction, but pi 2 is reverse direction, shown in figure C. Therefore, they cancel to each other, cancel the fluxes pi 2 set up by the end to end. So N1 I1 dash is equal to N2 I2. Therefore, I1 dash is equal to N2 by N1 I2, that is KI2. The formula is correct. Transformation ratio is equal to I1 by I2. Thus, totally conclusion, the flux is restored to its original value as shown in figure D. Therefore, total primary current I1 is the vector sum of I0 plus I1 dash. So primary current I1 is equal to no load current I0 plus leakage current I1 dash. So load conditional primary current is equal to no load current plus leakage current. So look at the phasor diagrams. So this may, suppose we have to explain offline classes, may easily understand. So as usual, first of all, listen clearly. Coming to the figure A, that is unity power factor, that is nothing but resistive load. Resistive load, voltage and current both are in same phase. As usual, flux is taken as reference, and the induced EMF E2, that is also equal to V2, and induced current I2, both are in same phase. Why? Because resistive load. So whenever we are connecting a load and secondary current is flows through the circuit, right? So that is I2. Because of this, this I2 secondary current and secondary induced EMF both are in phase for resistive load. And as usual, V1 is always opposite to that of E1. Now the primary current I1, is the sum of, generally sum of no load current plus I1 dash. I1 dash is produced because of pi 2 produced in the secondary, and it is produced in the primary winding. That's why it is in phase with V1. I1 dash is equal to V1 dash, and I0 is always like this, because sum of magnetizing current and no load current. Now combination of vector sum of these two, vector sum of no load current and primary leakage current is nothing but primary current I1, right? Why we have to draw I2 is here and I1 dash is exactly opposite of I2. Generally, why we are drawn I2 in phase with E2? This is a resistive load, right? That's why I am drawn in phase with E2. Now I1 dash, that is leakage current. Leakage current occurred because of I2 only, right? Leakage current is occurred because of pi 2. Pi 2 is occurred because of I2. That's why I2 and I1 dash both are in opposite to each other. That's why first of all you have to draw I2 in phase with E2. Then I1 dash is in exactly opposite to that of I1 dash, I2. And as usual I0. The combination of I0 and I1 dash is nothing but I1, right? Coming to the lagging power factor. Lagging power factor, current is lagging by voltage with some angle. So before one, both are in phase. Now coming to this one, I2 is lagging with some angle pi 2 by E2. I2 is lagging with some angle E2 by pi by E2, right? Now for this I2, you have to draw an exact opposite phasor diagram, that is I1 dash, right? Exact phasor I1 dash, and I0 as usual. Combination of these two is nothing but primary current, right? Now coming to the leading capacitive load. Current is leading with some angle pi 2 by an voltage E2 here. Pi 2 is leading with some angle pi 2 by E2. As usual, leakage current I1 dash is always opposite to that of I2. You have to draw a phasor diagram that is exactly opposite to that of I1, I2. Now, common vector sum of I1 dash and I0 is nothing but I1. Right? So, in this manner, we have to draw the phasor diagram for different loads: resistive load, inductive load, capacitive load. For resistive load, secondary current, secondary voltage, both are in phase. And primary leakage current is produced because of secondary current. That's why you have to draw the exact opposite to that of I2. I1 dash is always opposite phasor of I2. And combination of I1 dash and I0 is nothing but I1. For lagging current is lagging by angle pi 2 with voltage E2, and exact I1 dash, combination of these two I1. Similarly, this also. Now go for the equivalent circuit of a single phase transformer. For effect winding resistance, E1 is equal to V1 minus I1 R1. As usual, we know that V2, from that V2 is equal to E2 minus I2 R2. Now equivalent resistance is nothing but total copper losses is primary winding copper losses plus secondary winding copper losses, that is I1 square R1 plus I2 square R2. From that I1 square is common, taken as common, R1 plus I2 square by I1 square R2, but I2 by I1 is nothing but 1 by K2, 1 by K, I1 square R1 plus 1 by K square into R2, where the equivalent resistance in the secondary refer to the primary is, that is R1 plus R2. That means refer to the primary, that equivalent resistance secondary refer to the primary is nothing but we have to transfer the secondary resistance to the primary resistance. Original primary resistance is R1. Now the transferred resistance from secondary to primary is R2 dash, right? Now totally equivalent resistance refer to the primary is R1 equivalent. Do you understand? So primary resistance is there, that is R1. Secondary resistance is there, that is R2. Now refer to total equivalent resistance refer to the primary is in the sense primary resistance is placed as usual, but secondary resistance is transferred from the secondary to primary, that is R2 dash. So R equivalent, R1 equivalent is equal to R1 plus R2 dash, that is equal to R1 plus, we know that R2 dash is nothing but R2 by K square, R2 by K square. Similarly, equivalent resistance refer to the equivalent resistance in the primary refer to the secondary, that is nothing but R2 is equal to, second resistance is put in same manner, but we have to transfer the primary resistance from primary side to secondary side, that is R1 dash. Therefore R1 equivalent is equal to, R2 equivalent is equal to R2 plus R1 dash, that is R1 dash is equal to K square into R. You have to take in some identification, refer to the primary by K square, refer to the secondary into K square. K is nothing but transformation ratio. Now look at the figure. Individual resistance, this is R1 and this is R2, right? Now refer to the primary means primary resistance put in same manner, but secondary resistance is transferred to the primary, that is R2 comes to this side in the form of R2 dash. Now combination of these two is nothing but R1 equivalent. Now refer to the secondary means primary is transferred to the secondary, that is R1 dash. Now total equivalent resistance in the secondary is R2 plus R1 dash, right? To transfer the one resistance to another side. Refer to primary means secondary is transferred to primary. Refer to secondary means primary is transferred to secondary. As usual. So similar concept is used to reactances also, leakage reactants. Equivalent reactants refer to the primary. X1 equivalent is equal to X1 plus X2 dash, X1 plus X2 by K square. Primary refer to the secondary means X2E equivalent is equal to X2 plus X1 dash, that is X2 plus K square X1, not K2, this is K square X1. Now total impedance, we determine the resistance, we determine the reactance. Now combined combination of resistance and reactance is nothing but impedance. Equivalent impedance refer to the primary, Z1 plus Z2 dash, that is Z1 plus Z2 by K square. Refer to the secondary, Z2 plus Z1 dash, that is Z2 plus K square into Z1, not K2, this is also K square. Now look at the figure. R01, R1 plus R2 dash, X01, X1 plus X2 dash. Combination of R01 plus JX01 is nothing but Z01. Similarly, refer to the secondary, R02, R2 plus R1 dash, X02, X2 plus X1 dash. Combination of R02 and X02 is nothing but, so equivalent impedance refer to the secondary, this one is equivalent impedance refer to the primary. Now this is the equivalent circuit. We already discussed this one at no load condition, that is nothing but whenever the no load branch parameter R0 X0, shunt branch parameter, whenever you are applying a alternating voltage or alternating supply to the primary winding of transformer, no load current is flowing through the shunt branch parameter. That no load current may be split into two parts, that is working component and magnetizing component. So working component that is nothing but IC or IW, magnetizing component is nothing but IM. Now we have to find out. Now we have to find out these parameters. R0 is equal to V1 by IC, X0 is equal to V1 by IM, right? So what is the IM, magnetizing component of current, that is I0 sin pi naught. What is IC or IW, I0 cos pi naught, that is equal to active component of current. So this is the transformer equation. Now this is the total equivalent circuit for a loaded transformer. So supply voltage is V1 and equivalent resistance in the primary, that is R1 X1, current is I1, and shunt branch parameters R0 X0, shunt branch currents IW and I magnetizing. Combination of these two is nothing but I0, and primary current I1 is a vector combination of no load current and magnetizing component of current, that is I1 dash, leakage component of current. I1 is equal to I0 plus I1 dash. So secondary branch parameters, that is R2 X2, resistance, secondary resistance and secondary reactance, and I2 V2, right? These are the reduced equivalent circuit. We know we have to transfer the primary parameter into secondary. That means we can call it as referred to secondary. Suppose we have to transfer secondary parameters into primary, we can call it as referred to primary, right? Now, because of that concept is applicable to a equivalent circuit, that means the complete equivalent circuit of a single phase transformer may reduce it into approximate equivalent circuit of a single phase transformer. That means transferred, how to utilize transformation of parameters from primary to secondary or secondary to primary, right? First of all, we have to referred primary side. That means referred to primary means we don't change the primary parameters. Primary parameters are put same values, that is primary resistance and primary reactance. R1 and X1 is same. Now to transfer the secondary resistance and secondary reactance to primary. That is the called as refer to primary. We know that R2 dash is R2 by K square, X2 dash is X2 by K square, right? Where K is the transformation ratio and Z2 dash is also Z2 by K square. Therefore, from equivalent circuit, E2 dash is E2 by K, I2 dash is equal to K I2, right? R1 X1 is always there and R0 X0 is there. Now this secondary side parameter will transfer to primary side easily. Now primary parameters are transferred to secondary. That is also another approximate circuit. The complete equivalent circuit may be reduced to refer to primary or it may be reduced to refer to secondary. So this is referred to secondary. That means we don't change the secondary resistance and secondary reactance R2, X2. We just transferred primary resistance R1 and primary reactance X1 into secondary, that is R1 dash, X1 dash. And no load parameters R0 dash and X0 dash. So look at so refer to primary, we don't change R0, X0, we don't change R1, X1, but we change the secondary parameters R2, X2 to primary, that is R2 dash, X2 dash. Now combine these two. R1 plus R2 dash is nothing but R01, equivalent resistance refer to the primary. X1 plus X2 dash, equivalent reactance refer to the primary, right? And V2 dash, equivalent secondary voltage refer to the primary, that is V2 by K, right? That may be reduced to this figure. The above figure may be reduced to below figure. So R01, X01, that is Z01, R0, X0, V2 dash load. This is the equivalent circuit of a single phase transformer referred to primary. Similarly, so where what about R01? R01 is equal to R1 plus R2 dash, that is R1 plus R2 by K square. X01, X1 plus X2 dash, X1 plus X2 by K square. Z01 is equal to R01 plus J X01, right? So similarly, suppose go for the secondary also similarly. So X02, R02, X02, that is Z02. R02 is equal to R2 plus R1 dash, that is equal to R2 plus R1 K square. X02 is equal to X2 plus X1 dash, that is X2 plus X1 K square. So Z02 is equal to R02 plus J X02, right? Thank you one and all. So today class, this is about today class. Next class we go for the another topic of a single phase transformer. For this, in this class, we discuss about mainly we discuss about what will happen if there is no load. What is the functionalities of single phase transformer when it is a no load condition? What is the function of transformer when it is a loaded condition? And how can you draw a equivalent circuit? And also draw the phasor diagram for different loads in the loaded condition. Right? Very important question. Very important. Explain the transformer on no load and load condition. So this is the question coming from your JNTU examination, right? Today class is very important. So as usual, no load current is a splitting into two components, that is active component of current or core loss component of current and also magnetizing component of current, right? And another one, IW is equal to I naught cos pi naught, IM is equal to I naught sin pi naught, right? And power factor IW by I naught. And also you have to find out input V1 I naught cos pi naught. A loaded condition, you have to draw the different phasor diagrams. That is for resistive load, what is the phasor diagram for inductive load and capacitive load? Resistive load, the no load, the secondary current is in phase with secondary EMF. The leakage current is always opposite to the top secondary current. Lagging loads or inductive loads, secondary current I2 is lagging with some angle pi 2 by E2. Leading, it will be leading with an angle pi 2 by E2. Right? Thank you one and all.